Well, thank you very much, Mr. Chairman. I'm very happy to be here. I have to thank the organizers for inviting me here, in particular, of course, Andrei Janshinsky and Jean-Luc Tifo. They've been very kind. It's always a pleasure to be back in Cambridge. So this is a joint work with Simone Zuccher at the University of Verona. And as you see, I'm going to talk about aspects of vortex dynamics that are associated with a particular type of equation that takes care of quantum defects. And I'll do that by focusing on aspects that are, yes, geometric and topological, but I'd like to point out the connections with the physics, because otherwise Andrei would stand up and leave immediately, and to show you that maybe we have some interesting information to decide about a particular evolution rather than another, and that is related to the comment that Dewitt-Sumner's made in his talk. Okay, the summary. So we have lots of beautiful surfaces in playing an important role in biology, in chemistry, in physics, of course. So the first few slides is just to keep track of some aspects that might help us to infer physical properties. I will particularly focus on the evolution of a Hopf link of quantum vortices. So I go back for a moment to defects. So one-dimensional systems controlled under the GPE, this Gross-Pitaevskii equation. I'll then move to consider writhe and twist helicity contributions. And then I go from defects to surfaces that are bounded by these defects. So Seifert surfaces, and in particular the interpretation of this surface twist in terms of axial velocity flow for these filaments. Then I will recall a result that I introduced some time ago on linear and angular momentum from signed area information, and I couple this information that is, say, of a physical nature to the geometric information associated with these surfaces, and in particular the role of these minimal surfaces in this evolution. All right, so this slide is a very, very simple and of a general character. It's just inferring physical properties from shape. We all know that these are quite important. In particular, maybe the properties associated with formation of certain type of high curvature regions. Sometimes these surfaces play the role of optimizing energy, like we have in combustion. So it is quite important to think of this surface as a surface that optimizes certain type of chemical reactions, but also the fact that these surfaces may form very complex networks or topologies, and again characterizing the complex geometry or topology of these surfaces is also a quite interesting piece of work. And we know that these surfaces may minimize say tension, surface tension, like soap film bubbles. So it's interesting to focus, maybe to think of these soap films as a good example, and to keep it in mind. Surfaces may rise in field theory. This is an example of an old paper by Batty and Sutcliffe on high energy modeling of reconnecting structures, and these surfaces are just a way to depict change of topology. But surfaces occur also in other contexts. Of course, we have current sheets, magnetic sheets as well. This is just a picture from a satellite on a gigantic flare from the sun, and we see this formation of braided patterns of plasma loops, and through reconnection and through interaction of these structures, we may have current sheets forming also in plasma physics in confined environment like tokamaks, etc. These are quite important aspects.
Renzo,
Yes?
So patterns on the bottom of the swimming pool on a summer day, right? These are these also fitting into your theory?
Yes, these are also these defects are optical defects, and this is a similar kind of, yeah, absolutely. I wouldn't call it, a man, Robert Keane, I think, gave a name to these defects, but I think they are old as nature goes, and were known to Newton, I think.
Yeah,
so, yeah, the caustics and the surfaces may help to detect intensity of field lines or field distribution, like these are just iso-vorticity surfaces for two pieces of vortex tubes reconnecting. This is a typical bridging mechanism as visualized by this work of Hussein and Duraizmi. And then we have also surfaces arising in defect physics. These are just two vortex quantum vortices in under Gross-Pitaevskii, and these are the kind of surfaces that I will focus on. All right, so a very brief recap of what is the background. We have we think of vortex lines as a start, as a phase defects, and the function is a wave function that controls the evolution. The wave function psi is a complex function and can be written in terms of density rho, like mass density, psi squared, and then a phase theta. The grad of the phase can be interpreted in terms of a velocity. A velocity like a usual velocity, classical field. This is the equation I have in mind. This Gross-Pitaevskii equation is one of these equations that are non-linear. This is the time derivative of this psi function, and this is the second derivative in space plus the non-linearity here. So it's like the non-linear Schrödinger equation. We take in the numerics this assumption that psi squared goes to 1, rho goes to 1 as the position vector goes to infinity, and of course we don't have later on in the numerics infinity. We have a box that has to be far away, as far as possible, from the evolution we want to study, and I'll show you that this is also a difficulty that has to be overcome. The size of the box, of course, matters compared to the phenomenon. What is interesting about Gross-Pitaevskii is that you go back to these two variables and the physical meaning, and you can, as an exercise to students, you can ask them to decouple the real and imaginary part of this GPE, and you find that one part leads you to the continuity equation, the classical continuity equation, and the other part is very much similar to the Navier-Stokes equation, except, well, you have the minus the gradient of the pressure term, plus this term that plays the role of dissipation. It's not right exactly the same. It's called quantum stress, but it plays the role similar to Navier-Stokes. In other words, you may think that this is not so important when the defects are well separated and distant one another. When, however, these defects are approaching one another and eventually reconnect, then this becomes the relevant part. It's very little understood, so there is some work going on to understand in detail the role of this part. These defects are really defects, are intersection of isophase surfaces, And if you think of a scale, these defects would be on the scale of Armstrongs. We have a number of conserved quantities. The system is not integrable, so we don't have an infinite number of conserved quantities. But in this context, one important quantity is the Hamiltonian given by kinetic energy and interaction energy.
So how do P and tau appear?
Pardon me?
How do P and tau appear?
How?
How do they appear, P and tau?
How do they appear?
Yeah.
These quantities?
Yeah. P, I remember P is a very strange function, and I...
Right. I wouldn't know now to tell you. I can't remember. I have to check. These are very well known. And by the way, the fact that these quantities are constant, this fact is used to check also on the numerics. Maybe Hyder Salman may comment on that later.
The modulus of psi to the 4. So it's like the density squared.
Right.
And tau is the Laplacian of square root of rho divided by square root of rho.
Okay, helicity. Well, we heard from DeWitt's talk, helicity plays an important role. I have here the classical version of helicity is the velocity times the curl of velocity, which is vorticity. I'll take a divergence-less condition, and well-known result in classical ideal fluid mechanics is that this quantity should be constant. If I confine a vorticity to localized structures like tubes, then we have the result of Keith that we can interpret this quantity that is constant in time in terms of topology. And in case of a link, we have of course the Gauss linking number, and in case we have internal structure of field lines in these structures, we have this self-linking number, the Calugariano-White linking number, that can be further decomposed in terms of global geometric quantities. Gauss linking number, of course, is an old topological quantity. If we take, instead of two separate curves, one central curve and the neighboring curve, and construct the ribbon, as DeWitt showed, then we have the linking still well defined. We take the epsilon, the thickness of this ribbon going to 0, and we can prove, Calugariano proved, that this quantity is also topological invariant, but can be decomposed in terms of global geometric quantities, the writhe and the total twist. Total twist can be further decomposed in the total torsion plus intrinsic twist, but there is no need to go into that in my talk. Twist is just a measure of this ribbon unit vector, the span-wise unit vector twisting about the central line. Right, I need the ribbon in order to compute twist. I want to compute writhe. I want to keep track of these quantities during my interaction of defects. So this is the initial condition. I want to start with a Hopf link. In this case, the surfaces are visualized by rho equal 0.1. I actually go to rho much lower, and the evolution starts T0, and it evolves. Okay, so we have the two rings linked together. They move. At a certain point, they reconnect by antiparallel reconnection at a certain time. So from the Hopf link, we go to one single folded structure. We follow it up, and there is a further reconnection here. From these one single folded structures, I get the two separate unlinked, unknotted filaments, and we can follow the process further to the further decay into three unknotted, unlinked circles. I want to follow up this in terms of writhe and twist and helicity. So the idea was, as anticipated by DeWitt Sumners, to construct a Seifert surface and to detect the Seifert helicity on that. Now the interesting thing is that this Seifert surface, we can pick any surface we like, or in other words, we can pick any theta we like, and at a given theta, say theta star, I go all the way to the other defect. So if I keep track of my theta star, a particular isophase surface, I can construct on that a ribbon, and I can use this construction to work out twist. That avoids me to compute torsion that involves third order derivatives and lots of numerical problems. So I can use this ribbon to visualize the structures and to keep track of writhe and twist. All right, so very quickly I show you this is helicity that remains almost zero. There are jumps here, little jumps, and these jumps can be made even smaller if we enlarge the numerical box as far as possible. Of course, enlarging the numerical domain costs time, so this is a difficulty. The 3 points here detect the times of the reconnections. If we compute right, yes?
Why isn't that an integer? Don't you have discrete system?
Yes.
Why is the helicity not an integer?
Well, it stays almost zero.
Okay.
Almost zero. It's very hard. These are, you know, I can redo the numerics here and have these jumps even smaller. I still have little jumps from the numerical approximation. So I spend a few seconds to explain this. You have to think that all the times there are reconnections, there are kind of perturbations, either Kelvin waves or other, that are propagating away from the reconnection site towards, say, infinity. So towards the boundary of this numerical box, but the problem is that they come back. So they create some instability. If you enlarge the box, you can control better these systems. Okay, so if we look at the writhe, this is the total writhe, and the total writhe is computed using the formula that DeWitt has shown, writhe of each single individual plus eventually, or actually at the beginning, the linking, the Gauss linking. Of course, we have a change in topology as we go through these reconnection, and the physical information here is that writhe keeps decreasing all the time. Remember, writhe is a measure of, let's say, planarity, or the other way around, is a measure of three-dimensionality and folding. If the writhe tends to zero, it means that we are going towards systems that tend to be planar. Twist also decreases. Notice we have a minus sign here, and decreases consistently, and it jumps quite a lot through this reconnection. And this decreasing process is also quite interesting because it is related to energy information, or energy transfer information. Here I picked a surface, any surface we wish, and we can follow that. But it would be interesting to focus on particular surfaces. So I'll pause a minute for on these surfaces to tell you that we can interpret linear and angular momentum in terms of a sine area of projected graphs. This is the momentum, and this is the angular momentum, and we can rewrite these in terms of vector quantities, of course, but these vector quantities are related to areas. Areas of what? Well, I have, say, my link in space. I project the link on a plane, and I have to compute the area of this planar projection. But because I get a graph from a link in space, I have to come up with the definition of these areas. So I will call this area as a signed area of the projected graph, and the signed area along the I direction, say x, y, z, will contribute to the components of these quantities. I already picked a link. This is true for one single structure. It's also true for a network of structures. So a link would do. I want to dwell a little bit on this signed area to give you the idea and the hint of the proof of this. So I take my vortex line as an axis chi. Vorticity is just a uniform quantity along the tangent. This is circulation, just the flux of this vorticity across the section of the filament. The linear momentum is defined in this way, and I rewrite omega as in terms of tangent. This is dx des, arc length s, and then I extract gamma from this. So from a volume integral I go to a line integral, and then I consider the integral of x dx, which contributes to 2 times the area, whatever is this area. So I can rewrite this as gamma times this particular area, where this area is just the area whose boundary is the length of this axis. I have to take care of this area now, this calligraphic A. So I consider the projection, the component of the linear momentum along the I direction, and the area AI, calligraphic, is the area of the projected graph according to some definition. So I define this area of the graph as the standard area, or the contribution of each region of the graph in terms of standard area, times this index. And this index is a topological quantity, is the intersection number. Let's see how it works. So I have my graph projected from this space curve, and I identify the region, R1, R2, R3. I then consider the intersection number that I get from picking any point in this region along the radial direction outwardly, and I consider the right-hand frame with the unit tangent along this oriented graph, and then I assign a +1 or -1 according to sign convention. So in this case I hit this curve only once here, and according to my reference frame I have a +1. This +1 is this graphic I attached to this R1 region. I do the same for the second region. I intersect only one point here, and this would be 1. Mind you, I can take a point here and go all the way through another direction. The number won't be affected, is always the same number. All right, +1, I go for the third region here. I go into this direction, I intersect 2 points, and it happens from the graph I took that they are both contributing to +1, so is +2. Remember, I can go any direction I want, and no matter which direction I pick, I will end up with the same algebraic quantity. So these are the weights I associate to the area. So if the area is small, but the weight is large, that contributes to the momentum differently than if the area is small and the index is small. If the index comes to be 0, like a Hopf link projected with opposite orientation, then the internal region would have an index 0. That means it won't contribute to the linear momentum. If we shoot the 2 rings one against the other, it is intuitive to think that the linear momentum is 0, and indeed the area information would help to establish that. Okay, so we have this curly A now associated to the diagram, and we can establish this connection between the link in space and its interpretation in terms of areas, projected areas to the momenta.
Renzo, is it still true if you shoot the vortex rings at each other with an impact parameter that's not 0, so it's not on the axis?
Okay, very well. I showed in another talk actually here a few years ago. There is a beautiful experiment by Lim on. Let me just comment on that first, and then I come to your question. That you have 2 vortex rings exactly coaxially, and the result of that is that there are reconnections that trigger lots of sister rings inheriting the blue and the red from the original filaments, and you can see from the movie that they go oppositely and you can do these analysis, and you can work out the plus and minuses that are coming out from the system. They of course have to balance out because the linear momentum of the whole system is 0. So to get to your point, of course, if you have an unsymmetric collision, then you have areas of plus and minuses.
Linear momentum will still be 0, but the angular momentum will not be 0.
Oh, of course, of course. You have that too. You have that too from this analysis. You have the angular momentum with, you can identify an axis of rotation. And so you have what we may call an aerial moment contribution.
Yeah, that's interesting.
Okay, so now, yes, you say, okay, pick your isophase surface you wish, and you follow it. Now, this is one of the good news for this talk, because this is really work in progress. I want to switch to the movie, so I will show you the movie of the evolution of this surface, but which surface we pick? We pick a surface that has minimal area. So of the many isophase surfaces we have, we look for the minimal area surface. So this is the evolution. Okay, the beginning is nothing particularly interesting, except the fact that you see the role of the twist of this surface. Remember, you are always seeing a minimal surface evolution. This surface at a certain point gets stretched, and the stretching will induce a reconnection a bit lower here. You will see it in a moment. Okay, will appear here. The vortices are locally antiparallel. So a first reconnection takes place now here. It will, you see there is a kind of stretching of this surface, and this is due to the fact that this region has high curvature, and the curvature for vortex dynamics means high impulse. And then a second reconnection takes place here, and you can see really the evidence of this stretching acting on the structure, and then again we have a third reconnection taking place roughly here. Is barely visible, but it is again due to this curved surface. So I think the surface plays a good role to understand the physics. I told you we look at the minimal area surfaces, and so I want to go back to my slides. Well, first of all, a comment on reconnection. We have anti-parallel reconnection regions here, and these reconnections are more or less the same at various instances, like so, and this is in agreement in a sense with the talk of Dewitt-Sumner's. We have the interpretation of a surface twist in terms of velocity. I don't want to dwell too much on this. I just like to convey the idea that, of course, given a surface, because of this definition, the velocity, the fluid velocity, so to speak, should be thought of as the normal to the surface. If a defect is identified by a fan of these surfaces, that leads you to have, say, a circulatory velocity around the axis of this defect. This you can estimate from classical fluid dynamics. For example, in this case could be gamma over 2 pi r, r being the distance from the straight vortex. If you have a twisted surface and a fan of twisted surfaces, then you can associate twist in terms of axial flow along the filament axis. So this is also quite interesting to have a physical effect from the induced twisted surface. But this is the main result. The main result is that we compute the evolution of this minimal area versus time. And we saw that for the evolution I showed you, this minimal area keeps decreasing all the time. I know what you're saying. You're saying, well, here is actually not quite decreasing, is coming up again. We have the 3 reconnections taking place here, and indeed the blue curve is just enlarging the numerical box. Enlarging the numerical box size means that you can do a bit better on this region. We still have problems here, and we believe, we are pretty confident that this actually increase in area is purely numerical. It's a numerical problem that we want to sort out by having more computational power in order to extend further the effects of the box size. We have a little effects in the box size at the beginning, not visible, because you have to just start up the initial condition. It takes time, the initial condition, to get to the boundary of this box and to revert back the information. And then at the end here, here, you have the problem that your structures are well separated, and so they move a bit towards, say, the numerical box. So you have to enlarge the numerical box in order to keep the distance from the defects the same as the beginning. All right, so we investigated the problem for more complex structures, and this is, as I said, ongoing work. And the problem is, as DeWitt said, that we are looking for a criterion, at least in this context, where we can trust, let's say, the GPE evolution, a criterion that justifies this topological decay. The topological decay can be detected by some polynomials, as I did with Xin Liu recently. But this is not enough. You want to relate the topological decay with energy, or some information related to energy, in this case linear momentum. We'd like to have a criterion to select which evolution nature prefers. So we tested, well, this is just a little information about the phase. Theta is the phase angle of the minimal surface as it evolves. This is time, so we take a gradient of theta in space and time, and we can infer something about the evolution. But this is the next step. The next step is the trefoil. We went to the trefoil. Remember the experiment in classical, in water, done by Kleckner and Irvine. You see a decay process from a trefoil to the Hopf link, to the unlink folded, and then to the 2 separate links. We can see the same thing here. We do see exactly the same process as by Kleckner and Irvine. We start with the trefoil knot. Again, we have the problem that as the knot evolves, then we have to take care of the boundary reflection of these perturbations. We went on to test other knot types of increasing complexity, and we could follow the same path. In other words, starting from a highly complex knot, the knot decays following the same cascade process we saw before, but the minimal area keeps decreasing all the time. So this is my final slide. So we have a trefoil knot here. If we start higher up in complexity, say the 2-9, the minimal area keeps decreasing. The 2-9 goes through a number of reconnections, and by 2 reconnections we go to the 2-7. The 2-7 decays farther through links and then knots to the 2-5. The 2-5 decreases farther to the 2-3, and the 2-3 decays farther to the Hopf link, etc., etc. So all this pattern is confirmed under GPE, but what is also very nice is that we can track this evolution or the whole cascade in terms of diminishing minimal surface. So this is my end message. This is work in preparation. Thank you very much for your attention.
So Renzo, in this cascade here, you see only 2 n torus knots and links. You don't see any of the other possibilities?
Now we see, so problem is we would see, I suspect we will see all the cascade stages. Problem in the simulation is that we have to Imagine that you configure the initial configuration, the initial data, and you want a torus knot that is not exactly symmetric, as is given by standard equations. Because if it is symmetric, then reconnections take place all at the same time, and you cannot detect all these stages. So you have to, how to say, perturb a little bit the mathematics, the initial condition, in order to see all the... This is the work we've done with the Hopf link. The Hopf link was set up in order to see one reconnection at a time. Because if you start with exact symmetric configuration, you don't see that happening. Now we can follow this cascade in the trefoil knot, and it gets so to perturb a little bit the trefoil knot and let it evolve. And as a start, we just checked first on the area information on more complex systems. So what you would do from the 2-9, would be a number of reconnection, maybe 4, maybe all of them together. So you don't want that to take place.
So I guess I have 2 questions. First is, does mod psi squared go to 0 and the reconnection?
Say it again.
Does mod psi squared go to 0 on the reconnection?
What do you mean?
You're doing right. You're doing Gross-Pitaevskii, right?
Right.
And Gross-Pitaevskii involves psi.
Right.
And the question is, it is a complex number. So this is the modulus of this complex number
Oh, right.
go to 0.
Yes. Yes, they do.
So how do you continue the velocity? The velocity is a gradient of a function, of an angle that's not defined.
Sure. You do not compute the velocity of course, on the defect. That's the singularity.
But how do you take the next time step?
Simone Zuccher might help you on this. I exactly don't know.
Well, the other question is, what about periodic boundary conditions?
Right. So again, so sure, I'm aware of those. The technical information is in the paper, on the Physical Review E paper of this year. I will give you all the information through the paper. Is a mirroring 8-fold the original box. That is the only little thing I remember, but I am not so good at telling you details of the. Sorry for this.
Renzo,
Yes.
you give a very convincing proof of what is actually, I think, quite well known, that the momentum of a vortex or a system of linked vortices is equal to the signed area.
Right.
So I don't see what's special. I mean, it doesn't depend on which area you choose, which surface.
Exactly.
So why does the minimal area surface be of any particular significance?
Perhaps because, well, of course, we don't know. We pick the minimal area because we believe it might convey some information on minimal energy. Not in terms of the momentum interpretation.
Yeah.
The momentum interpretation is irrelevant, which area you pick.
Okay.
So, do experiments in whatever system confirm this particular time scales that you obtain numerically?
I cannot comment right now on that. The time scale of reconnection has been checked by several authors, and so we are consistent with the results of others. Maybe again, Brachet has done work on that. Haider has done work on this. The time scale is of the single reconnection is consistent, yes, of course.
But you don't know for the cascade.
But this is not known, is new. So.
Okay, so thanks, speaker, again.
Okay, thank you.